At a construction site, a 22 kilogram bucket of concrete is connected over a very light frictionless pulley to a 375 Newton box on the roof of a building. So here we have a bucket that's 22 kilogram heavy, and we also have a box that have display as 375 Newton. Actually, it is provided the weight, and from there we can also find the mass thanks to the equation mg. Okay, so this is the system, and here we have a pulley, frictionless pulley, which means that along this rope on the tension is the same. Okay, there is no friction, there is no appreciable friction on the box since it is on roller bearings. So the roller bearings is not drawn here, but it just means that there's no friction here. Yeah, it's very smooth here, and the box starts from rest. So in reality, what could happen? We could imagine that if this is really heavy, it will keep pulling this one downward, right? So then the box will move towards the right. And they ask us to make a free body diagrams of the bucket of the box. Okay, so let's do this first. And again, just a reminder how to draw a free body diagrams. Again, what is a free body diagram? That is a diagram that's free of body, so no body shown, and what we need to focus on is just the forces. And in order to determine the forces, to draw them out, we have to focus on which body we are talking about, how many forces acting on the object, and then for each forces we need to identify these three features, like which act on which object act on which object, in which direction, and what is the magnitude. Okay, so this is a reminder, the foundations of draw a free body diagram. So here we have two objects, right? Maybe let's start on the bucket first, because it seems that it's simpler. So what added on the bucket, and now looking for something that in direct contact with it. Okay, whenever we do problems with forces, looking for direct contact. And here the bucket actually is in interaction with the earth, weight pulling it downward, always straight downward, and then in direct contact with the rope, so there should be some tension pulling it upward, right? So in here I haven't drawn the forces in scale, so the magnitude is not like explicitly indicated by the length. Okay, we just see that this is upward and this is downward. That's it. Okay, then we're done for the first object. Here it should be labeled as object number 2. Okay, then we can go to object number 1. So how many forces are there? Think about it. It's different from the bucket because it's placed on a horizontal surface, so there should be some other forces that keep it upward like this, right? If we don't have any force that keep it upward like this, it would just it should go down through this table or like this top. So there should be a normal force. Whenever it in contact with some surface, there should be a normal force that upward and normal to the surface. Okay, so here we have a right angle here, and we know that there's also some tension attached. There's also a rope attached, so there should be some tension, and this tension should be equal to the tension here. And then always weight, W1 just like mg1. Okay, so then we done. Because here we don't have friction, so we don't have any forces pulling in this way. If we have a friction, then the friction should go this way against the motion direction. So that's the question A.